Okay, so this is the business discussion for optimization. And I'm just going to kind of give one business discussion at the start of the optimization section for the two chapters. And the thing is with optimization, optimization is absolutely everywhere. We may want to um, maximize our revenue in a business situation. For example, we might want to maximize our revenue from hotel rooms by setting prices. We may want to minimize the time it takes for for Amazon, for our delivery lorries to go around to their destination. So we might want to set schedules to minimize the total time taken. In a regression model, which we've been doing a few weeks back, we want to actually minimize the error in our model compared to the actual data. So in the regression chapter and in the video examples I gave for the forecasting chapter, we're essentially to set our parameters, we're essentially running an optimization. So optimization is absolutely everywhere. Now, what exactly is optimization? We'll think of it a little bit like climbing a hill. So imagine that I work for a marketing department and I have two different variables that I could actually pick. Make it a very simple example. One is the amount of money I spend on advertising, and two is the amount of money I spend on customer service. And the idea here is that if we have our profit on the y-axis, there's one of these combinations of the two values that's going to give me the maximum profit. And essentially all an optimization algorithm does is it starts somewhere in this solution and it kind of keeps on going up the hill until we find the optimal profit. That's all we're doing. Now, you notice in this example, we have two hills. What happens if we go up the wrong hill? Well, that's a little bit beyond this class, but some optimization problems, there's one solution. And these are kind of often called convex optimization problems. And sometimes there's multiple what we call local optimas, which makes it much more difficult to solve the optimization problem. So again, the theory is a little bit beyond this class. There's different classes of optimization problem based on how hard they are. But the idea is you have a problem and you can think of it as climbing a hill, or if you've got a minimization problem, trying to find the lowest possible point. And you're basically trying to find some way of getting up the hill. And you're trying to basically find the peak point, which might be the maximum profit, the maximum revenue, something like that. Now, there's various different types of optimization problem. So if you look on the book on page 472, there's a little example of where we're making two different types of skis, the Jordanelle and the Deer Crest. And basically, there's an amount of profit associated with each of these skis. And what we have to do is we have to maximize the profit. So it may be we have the profit for 5 for Jordanelle and a profit of 4 for Deer Crest. And we're basically going to maximize 5 times Jordanelle plus 4 times Deer Crest. And that's a linear objective function. There are no quadratic log terms or anything fancy there. So a linear optimization model is your objective is linear. If we're dealing with regression, our objective is quadratic, it's not linear. So we have a linear objective function. And also all of our constraints are linear as well. So here we have Jordanelle takes, if we go to page 472, 3.5 labor hours, and Deer Crest takes 4 labor hours. And we say we have a total of 84 labor hours. Then we'd have 3.5 times Jordanelle plus 4 times Deer Crest is less than or equal to 84. Again, that's linear. And the third thing is that our variables are continuous. Now, in the case of making skis, you're not going to have 0.2 of the ski, but quite often, if we have thousands and thousands, we're making thousands and thousands of skis, um, we can kind of assume that we can just take the nearest number and we're still going to get a good solution. But overall, variables are continuous in that they can take any possible value. And the optimal solution could have, 179.8 Jordanelle skis. That means they're continuous. We can also have an integer variant of this, and that's just the decision variable can be an integer. So here, where we're picking the number of skis we produce for each of the brands, it has to be a whole number. Now, why wouldn't we always do this? Well, integer optimization models are much harder to solve than basic linear optimization models. So quite often, we'll do a linear optimization model and we'll approximate. We also have a special type of this problem where the variables can be 0 or 1. Now, to give you an example of this, we maybe have 10 different machines, and these machines can be on or off at any one time. So for each of these machines, we would have a decision variable, which was a 0 if it's off, and a 1 if it is on. And that is a binary integer program. But most kind of complex optimization models, they will generally have both integer variables and non-integer variables and kind of continuous variables. So we might have, the machines, we might have whether they're on or off, and then we might have how many items we produce on each machine, which would be continuous. So we can also have what we call mixed integer linear optimization models. So next thing, and finally, we have a nonlinear optimization models, which is basically anything where we have a nonlinear objective function. If we talk about financial portfolio management, we often want to minimize, we want to kind of maximize our return, but also minimize the amount of variance that we have in our portfolio. We don't want stocks that jump up or jump down by a lot. And the variance, as we remember with chapter 4, if you calculate the variance, that's actually quadratic. So that would give me a quadratic model. That would be a nonlinear optimization model. But for this chapter, we're sticking with linear optimization models. And finally, I put this one in myself because I think it's kind of quite important, in that there's two major classes of optimization model. There's deterministic optimization and stochastic optimization. Okay, so for deterministic optimization, let's just start thinking of an example. So we have an optimization problem, and one of our inputs is the cost of a certain component. And we've already bought that component, so we know it's going to be $5 per unit. Then that's deterministic. And generally, if you don't think you're going to have a large amount of variation in your inputs, then you might want to use a deterministic optimization problem because it's so much easier to solve than a stochastic optimization problem. And basically, if we have that situation, going back to my little hill climbing example, if we have one peak on the hill and we have this, single good solution to the optimization problem, we're going to get the same solution that pretty much every time we run the problem. The other type of optimization is stochastic optimization. And here, the input parameters basically have a random component. So imagine that we're producing instant ground coffee, and our input is coffee beans, the cost per pound. Now, coffee beans can vary in price quite dramatically from week to week, month to month, depending on crop failures, weather, etc. So we might decide that, hey, we want to have some sort of leeway in this model, variation in this model. So we model the cost as having a mean of $5 and a standard deviation of 1. We also might say which distribution this comes in. So we'd say it comes from the normal distribution. And our results can actually be used in terms of, given in terms of distribution. So we might have a distribution of our profit distribution. We might say we have 95%. Confidence interval for our profit of the optimal solution is between, say, $700,000 and $800,000. Stochastic optimization is used a lot when we have to consider demand inputs and we don't know exactly what the demand is going to be. So another example, imagine we're selling, frozen ice cream, and it varies very much. Your sales vary very much based on the weather. And we want to build kind of a supply chain optimization algorithm for our frozen ice cream. Then it might make sense to have demand as a stochastic parameter because it varies so much. We cannot be certain of it. So here's my little kind of summary. Most real world problems, there's going to be, the real world is not deterministic. When I get up in the morning, I don't know exactly what I'm going to do in my day to the nearest second. But deterministic optimization is simpler. It's much easier to interpret, i.e. we have a predicted profit. We have amounts of each kind of, if this is a production problem, we have the amounts of each product that we're going to create. So there really is this trade-off between detail of a stochastic model and parsimony and easy interpretation. Though I will say modern revenue management, supply chain applications, there has been a big growth in stochastic optimization over the last 10 to 20 years. And here from the book, these are just some general examples of linear programming models. And it's kind of quite interesting because it gives the product mix, the decisions, the objective, and the types of constraints. So we actually have here, we have the product mix model. We determine, this is basically the example on page 471 and 472. We've got a load of different products. What combination of these should we produce and sell? And we want to maximize our profit. And we have resource limitations, for example, production time, labor, material. We might need to produce a minimum amount of like one product or a maximum amount of another product based on our sales potential and requirements. So we have various different business constraints. Sorry, I just hit the mouse button. We might have process selection, very similar. How much of the product do we make using different processes? Blending a product. How much of each material should we make to produce a unit of the output product? Portfolio selection, that's an interesting finance application. We want to maybe maximize reward while minimizing risk. So we want to kind of, decide how much we want to invest in each sector of the market, or how much do we invest in stocks, how much do we invest in bonds. And we want to maybe have some combination of maximizing return and minimizing risk, subject to, we might want, for example, not to put all our money in stocks. We might have a limit of 50% in stocks because of the risk profile of our funds. We might not want to have, say, more than 20% in any one sector. Transportation planning. Maybe we have different factories all over the world and different kind of consumer centers where we need to deliver our products. And basically, we're just trying to minimize our total transportation costs based on things like ship capacities, the amount of demands at different of our destinations, production planning, how much do we produce of each product in each period. These can get very complicated very quickly once you have additional period variables. And we want to basically minimize the production costs. And we have certain things like, we might need to produce a certain amount of products at certain times. We have limits on how long our machines can run for before being needed to maintain. We maybe have labor constraints, employee constraints, and things like that. And again, this is basically similar to the portfolio amounts to invest in certain investments. And production in marketing. We may, for example, decide, hey, we've got, search engine advertising, we have social media advertising, we have traditional media advertising. How much do we spend on each of these in order to maximize profit, related to maybe budget limitations? And again, we might want a certain amount, minimal amount on on each of the categories, minimal amount of social media, a minimal amount on SEO advertising, etc. Okay, so let's just look at the model on page 471. And, I won't spend too much time on this. This is really nice and really clearly done in the book. So we need to determine what we're actually going to decide in any optimization model. So if again we go 470 to 472, we have two different brands of skis, and we want to know how many of each we need to produce. We need to have an objective function. And the objective function is we make a certain profit on each of these brands of skis, so we want to maximize our profit. Then we need to understand our constraints. So for this example, we have labor constraints. The ski that gives us more profit takes a little bit more labor. So we actually have a constraint with regards to the total amount of labor. We also in this example have the finishing constraints and other labor constraints. And we also have, we don't want to make all of the same brands. So we might say, for example, in this example, that we need to produce at least twice as much of one brand as another brand based on our previous estimates of what we need from the market. Okay, so a few of topics of my own. How do we actually solve optimization problems? Well, the answer is with optimization algorithms. In this class, we are not creating optimization algorithms because they require lots of linear algebra and lots of calculus. And we don't want everybody to drop out of the program. But if you were to take an optimization class, say in industrial engineering, then you would be basically doing quite a lot of math. Now we're going to be doing it using Excel Solver. Solver is quite a powerful tool, and it is integrated into Microsoft Excel. But one thing we note is that Solver is actually a cut-down version of a commercial package called Analytics Solver by Frontline Solver. So this was obviously not created by Microsoft. There is a company out there that produced Solver, and they've basically supplied a really kind of cut-down version to Microsoft for Excel. And of course, given the installed base of Excel, it's basically like a little bit of free marketing. It's almost like consider it a trial product. So in Solver, we're limited to 200 variables and 100 constraints. Now that doesn't seem very much, but if you have like different factories, different periods, lots of different products, for a commercial enterprise, this is probably not going to be enough. You can really build up variables and constraints very, very quickly. So the full version of Solver, basically, you're allowed, for linear optimization, you have 8,000, and for nonlinear, you have, because it's much harder to solve, you have 1,000. So if you're to buy the full version of Solver, then you would get more. Now, what you could also do is we have specific, what we call solver engines. And basically, these solver engines, they're not specific to Excel. They're basically, we send them a problem in a certain format, and they will solve the problem for us. Now, different solvers are better at different tasks. Some are really, really good on linear programs. Some are really designed to solve integer programs or binary programs. Others are designed to solve nonlinear programs. So some of them do everything pretty well. Other solvers are designed to do a specific task really, really well. And again, a little bit beyond the scope of the class, but just be aware there's all these things called solvers out there. These days, usually accessed through the cloud on very powerful computers. And if I'm running, say, my analytics solver, and my problem is too big to solve within that solver, I can send my problem off to one of these online solvers, which of course might cost me a little bit more money. And you can see here that these solvers, the basic one has 32,000 variables and constraints, and the other ones are just basically limited by processing power. Now, it's all very well doing it in Excel, but imagine we have 1,000 different products, and we want to know how much to create of this. Well, that's 1,000 columns in Excel. And if we have 1,000 columns times 100 time periods, then that's 100,000 columns. So you get what I'm saying. Excel really is not feasible to model kind of very complicated problems. For example, production with lots of products. So for that, you would actually utilize a dedicated optimization language. I've listed 3 of them here. I've utilized AMP. I've done a course with Ample in the past. I've also played a little bit around with Minisync. But the idea is we define our product, but we define it on these things called sets. So we'll say, okay, we have a set of products, and then we'll say, for example, to maximize our total profit, we will sum across all the products the profit from each product times the amount we make. And then we'd actually pass it a data set with all the details, all the costs for these products. So literally we could have 100,000 variables here, but we only have 10 lines of programs, and then we send it the data set. So that's an optimization language. And generally, if we're passing big programs to these solvers, we would use one of these languages rather than using Excel. But that's like way beyond the scope of this course. So here's another example, and this is an example of a non-linear optimization that we've actually done already. In that with regression, what we're trying to do is we have a regression line, and we're trying to make our data points as close as possible to that regression line. We're trying to minimize the error. And I kind of gave this as an example. If you go back to the regression chapter, I started with a big video where I kind of drew an example for this. So here we have our kind of fitted equation by y hat equals beta 0 plus beta 1x. And for each kind of data point, we have a difference between the data point and the actual regression line. This is the error. So the sum of squared errors is the sum of all of these things. And basically, it's the sum of the differences between our y and the fitted regression line. Now we have to actually square that so that the distances, the negative and the positives, don't cancel out. But essentially, we've got an optimization problem where our decision variables are our beta hat 0 and our beta hat 1. And we're trying to change those variables in order to make our line, or all the y hats on our line, similar to the y's. So regression is actually an optimization problem, and most kind of machine learning methods similar to regression are also optimization problems. So don't worry too much about the math, but just realize again, when we run all these methods, that's why I try and do some examples in Solver. We're actually doing some sort of an optimization problem. So I just kind of finish with a few example dashboards, because for the average corporate employee, they are not creating optimization problems, but they will be utilizing optimization problems. And generally it will be done through a dashboard or some sort of application programmed by someone else. So the first example is route planning. Now, a simple route planning is when you go to Google Maps and you plan your best journey between 2 points. There's a degree of optimization here because we're optimizing to minimize the time. But we also might set some constraints in that we might want to avoid certain things. We might want to avoid toll roads. And it's real time. Your optimization algorithm kind of updates as you go along with your route. But imagine that you were not just somebody traveling from A to B, you were actually a delivery company and you had certain deliveries that you had to do throughout the day. So you would have a problem where you'd want to optimize. Maybe you'd want to minimize the distance, minimize the time, minimize the route cost, but you have constraints on the number of vehicles, your availability of employees, the route times, route distances, etc. So here we have a few dashboards. This is an example from one of the dashboards of an optimization system for route planning. But again, you're not doing the math, you just see the dashboard. My second example, and again, I give you three. For each of these, I want to just give 2 or 3 commercial implementations. This is sales territory management. Maybe we want to minimize the distance traveled by the salespeople, minimize some sort of cost, try to make our territories as compact as each other. But we, some of these things we could either have as variables or constraints. We could have constraints that no territory is more than 20% bigger than some other territory or something like that. So again, if we want to split up a certain region into sales territories based on distance, cost, the amount of revenue available within that region, then we can do it with sales territory management. And again, it's really just an optimization problem. Now, I thought this was I had to give this example because something at the moment is redistricting, and it's all very controversial on the news. And basically, it's done to maximize political gain, but people say, hey, maybe we should optimize for fairness. So we actually have 2 different kind of optimization parameters here. We have the median seat, the difference between the partisan lean of the state, and the difference between the median district. An unfair map, what you would do is, say, for example, you wanted to have it for, in favor of the Democrats, then you would have one Republican district that was like all the Republican voters were stuck in with plus 50 Republican. And then you would have lots of narrowly plus 5 Democratic districts. So here, maybe it was a 50-50 state, but the median district would be Democratic. So that would be this median seat thing here, the difference between the median seat and the overall lean of the voters in the state. And there's also the efficiency gap, which is basically the number of wasted votes, the ones that don't go. So it's the difference between the votes gained relative to the number of seats gained. So there's lots of applications here, and these are actually quite fun to play around with. Some allow you to create your own districts, some optimize. And you just think like Congress down to councils, we want to optimize, the fairness of our seat. We might want to optimize with respect to compactness. But we've got constraints that all districts need to have the equal population. And there may be voting rights act constraints, i.e., minority communities can't be spread through lots of different districts to dilute their voting power. And here was I thought we have the example of it's very hard to be fair with 4 congressional districts, but this is the Mississippi redistricting, and this was the redistricting that gave these values here. And this is 3 strong Republican, 1 strong Democrat. Revenue optimization. So unsurprisingly, we've got our friend William Shatner with Priceline. We're trying to optimize revenue, and we have constraints on number of rooms, types of rooms, etc. Now, quite often this would be a stochastic problem because we'd have to work, basically we would be setting our prices to optimize revenue, and we might want to kind of have to do this based on predicted demand. So there may be this would usually be a stochastic problem. But there's lots of different dashboards from a implementation side that allow you to do this revenue management. And from a consumer side, you can just play around with things like Priceline and see, revenue management is also very big in the airline industry. As a plane gets booked up quicker, the prices go up, etc. And then finally, we have production planning. There's lots of dashboards for that. So we can optimize the number of items produced, but we have constraints on capacity. We might have employee constraints if we need employees, maintenance constraints. Machines need to be maintained for a certain number of hours each day, maybe. And there's various kind of production scheduling software. Again, most of these pieces of software are not just optimization, but they will usually include some sort of optimization algorithm. And my last one, why we're kind of in scheduling algorithms, we've got one for employee scheduling optimization. So maybe we want to minimize our cost. We're at a supermarket, but we want to minimize, or Walmart, we want to minimize coverage constraints, i.e. we need a certain number of employees on at any one time, and this will depend on the demand at that time of date. We can't like work our employees more than a certain number of hours. We need to give them breaks. We need certain ratios of different employees. For example, we need a certain number of supervisors. We might need a certain number of deli staff. And again, we have a few different dashboards that allow us to do this. So I just finished with, I kind of started off by talking about optimization in general, types of optimization. We went through different ways of implementing optimization models, and I gave a few examples. I couldn't resist giving regression. And also time series analysis, which we did a few weeks ago. That's very similar. I actually added some of my own stuff. I showed you how to actually optimize the parameters to minimize error, optimize the smoothing parameters, the alpha, beta, and the gamma. And then I went through just what I thought was some kind of quite interesting optimization applications using different dashboards. Okay, and that's it.